Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to learn how to name organic compounds that contain amines as its main functional group. Before we get into the details of naming these organic compounds, we need to understand the structure of amines and where they come from. And so amines are another class of functional groups in which it is derived from ammonia or NH3. And so if we draw the Lewis structure of ammonia, we can see that the central nitrogen is covalently bonded to 3 hydrogens and 1 lone pair. And so it turns out that if at least one of these hydrogens is replaced by a carbon chain or an alkyl group just in general, then this ammonia is then recognized as a functional group called an amine. And so we can classify amines based on the number of alkyl groups or R groups or carbon chains that's bonded to the central nitrogen. And so this method of classification is analogous to or synonymous to alcohols, where we have a primary alcohol, a secondary alcohol, and a tertiary alcohol. However, the biggest difference between the classification of an alcohol to that of amine is that we're looking directly at the number of alkyl groups that's bonded to the nitrogen atom. Whereas in the classification for alcohols, we had to look at the carbon that the alcohol was attached to for us to be able to determine if it is a primary, secondary, or tertiary alcohol. All right, so basically, if one of these hydrogens, and only one of these hydrogens, gets replaced with an R group, then what we get is a primary amine. And so whenever you guys are drawing or thinking about primary amines, this nitrogen, the central nitrogen, has to have 2 hydrogens and only 1 R group and a lone pair. And so the general structure of a primary amine is going to be RNH2. Now, if I move to the structure to the right of the screen, a secondary amine is represented by a central nitrogen that is covalently bonded to 2 R groups. And so these 2 R groups can be the same alkyl chain, or they can be 2 completely different organic compounds. And so whenever you guys are drawing secondary amines, you have to draw the heteroatom nitrogen with a lone pair, but you cannot draw 2 hydrogens. You must draw 1 hydrogen for a secondary amine. And so the general structure for a secondary amine is R2NH. So notice that as we increase our classification, so primary to secondary, we're decreasing the number of hydrogens with respect to the original structure, which is ammonia. So looking at tertiary amines have 3 different R groups that's covalently bonded to the central nitrogen atom. There is still present on that central nitrogen atom a lone pair. However, there are no hydrogens that's covalently bonded directly on that central nitrogen. And therefore, the general structure of tertiary amines is R3N. So in short, to summarize, the primary, secondary, and tertiary amines has the presence of the lone pair on the nitrogen atom. And it can be omitted when you guys are drawing either condensed structures or skeletal structures. Much like we omit the lone pairs that's on an alcohol, the oxygen on the alcohol, when we draw it using the skeletal structure. But we just need to know in the back of our mind that it's there. Remember, our carbons, oxygens, and nitrogens, as well as fluorines, must follow the octet rule. And so quaternary amines are also possible. And this is, my screen is freezing again. So quaternary amines are possible. However, what happens is that it is the lone pair that's going to bond to another lone pair that's going to be bonded to another R group. And so because the nitrogen has to give up one of its electron to make a covalent bond with an R group, the charge on the central nitrogen changes. And so if there are 4 alkyl chains, they can be the same or different, that's covalently bonded to this central nitrogen, then the charge, the formal charge of that central nitrogen is going to be positive. And so this is an example of a quaternary amine. So notice that there is a positive charge on this central nitrogen. And there is no lone pair that's present in a quaternary amine because that lone pair, one electron from that lone pair, was used to create that covalent bond between the nitrogen and the 4th R group. And so overall, we can go ahead and compare and contrast, the differences in the classification of the amines. And so here we have ammonia with all hydrogens. And then if we replace one of the hydrogens with an R group, for example, a methyl group, we get a primary amine. So notice that we have CH3 and H2. For secondary amines, we have 2 R groups and 1 hydrogen. For tertiary amines, all of it will be an R group. And so down below is just a ball and stick model to give us a 3-dimensional view of what these organic structures look like with amine as its functional group. So here we can see the tetrahedral feature for the carbon of that alkyl chain, as well as the tetrahedral feature or trigonal pyramidal feature, if you're talking about it in terms of molecular geometry, for this R group. And so, or for this amine. And so looking at this primary amine, let's talk about electron and molecular geometry real quick. Since we have 1, 2, 3, 4 groups of electrons, the electron geometry is going to be tetrahedral. However, if we're looking at it in terms of molecular geometry, where we're differentiating lone pairs from covalent bonds, we have 1, 2, 3 bonding pairs, and we have 1 lone pair. And so that's going to inform us that the shape is going to be tetrahedral, but more specifically, it's going to be trigonal pyramidal. And so overall, the geometry for tetrahedral and trigonal pyramidal is going to be approximately 109.5. So it mimics that of a carbon. And once again, my screen is frozen. Jesus. So now that we know the general bond angle that we're working with, we can see that there's some three-dimensional geometry for this amine, where if you guys are looking at this bond, it's kind of going behind the body of this central nitrogen atom. Whereas if you guys are looking at this bond, this hydrogen is kind of protruding above the plane of the nitrogen. All right. And so amines can also be found as part of the ring. And so this is known as a heterocycle. And so, for example, here, if we have an amine or a nitrogen that's embedded or part of the ring, right, we're going to refer to this specific amine as a heterocycle. And so in terms of structure and bonding of amines, I already mentioned this in the previous slide. It's going to be trigonopyramidal, and you guys can go ahead and look at the geometry using the wedged or bold line and the dashed line that's going behind the plane of the nitrogen. Okay. So when you guys are representing amines in terms of a skeletal structure, it's really important to draw in the hydrogen, the number of hydrogen that's present on the heteroatom nitrogen. And so, for example, if you wanted to draw a three-carbon organic compound that contains an amine, here we have 1, 2, 3, and then from that third carbon, we're going to link it to the central nitrogen atom, and we're going to have to write H2. Okay? We need to represent the number of hydrogens that's on these functional groups, much like we do for alcohols, for instance, or aldehydes. Okay? And so this is what a secondary amine looks like. And when you have a tertiary amine, notice that there are no hydrogens that's drawn because all of the available hydrogens were replaced by an R group. Okay, so I'm going to skip the polarity of amines and intermolecular forces. You guys can just go ahead and read that on your own. And we're going to go straight to, actually, I do want to cover this part because this part is pretty interesting. And so where are amines typically found? And so amines are typically associated to odors that are foul, such as like rotting fish, urine, and bad breath. And so if we zoom in on this structure here, we have putrescine. So putrescine is the name of the organic compound that's coming off of rotting meat. And so here you can see this organic compound of putrescine. Notice that we have two primary amines. And I know that I have a primary amines because I have NH2. And this central nitrogen is only bonded to one carbon. Okay? So feel free to use those indicators to help you classify your amines. And so here we have cadaverine, and that's also one of the foul odors that's coming off of rotting meat. And so cadaverine has 1, 2, 3, 4, 5 carbons. Putrescine has 1, 2, 3, 4 carbons. And if you look at the amine functional group for cadaverine, notice that we have a primary amine on both ends. And so if you guys like to eat fish, when you go to the fish market, you kind of get that nauseous, foul odor. And so that's coming from the trimethylamine. And so if you guys are looking at this organic structure, notice that all R groups replaced all hydrogens that were originally on that nitrogen. And so this is a tertiary amine. All right, so amines are also found in heterocycles. So for example, if you guys are looking at caffeine or nicotine, these are stimulants of this central nervous system. And so I'm going to zoom in on the structure of caffeine. And so I'm not too sure if you guys have seen this before, but some people who really love caffeine, they have a tattoo of this on their body somewhere. I've seen it on some people. There's also, for example, like mugs in which they have this organic structure as part of their design for that mug. So anyways, here we have 1, 2, 3, 4 nitrogen atoms that are embedded or as part of the heterocycle. And so if you wanted to classify each and every single one of these nitrogens, here we have 1, 2, 3 bonds, or all of those bonds are going to carbons. And so this is a tertiary amine. This is also a tertiary amine. This right here, it's going to be, well, there's still a double bond there. So this is still going to be a tertiary amine. And this is also a tertiary amine. Okay. And so nicotine, if you guys are looking at this heterocycle, here we can see another amine that's part of that heterocycle. So we have some functional groups that are found in morphine and codeine. So for example, here we have an ether, here we have an alcohol, and here we have an amine that's part of the heterocycle. And so morphine and codeine they're both found naturally occurring in the milk of poppy. So I'm not too sure if you guys have ever experienced frolicking through a field of poppies, but at some point in time, you guys can squeeze a bulb of a poppy, and this white stuff comes pussing out. And so this plant naturally produces certain amounts of morphine and codeine. I think if I recall correctly, there's more morphine in the milk of poppy than codeine. So there's a higher percent of morphine than codeine, but both are found in there. And so, it would be really convenient that if you guys went on a hike and accidentally like sprained your leg or did something, hopefully you guys are near a field of poppy, so that way you guys can lessen the pain that you feel. But overall, let's just hope that you don't injure yourself while you go on a hike. I think that's the best case scenario versus trying to hope that a milk of poppy is found in that area. And so I thought I would include this table for those who are going into nursing. So I grabbed this from the nclxquiz.com. And so this just, it's a quick reference chart that describes, the dosage, the frequency, the duration of the effect for some of these opioid drugs: codeine, fentanyl, hydrocodone, hydromorphone, and the list continues. Okay. So feel free to check this out. What's really interesting about morphine is that if one was to be like, an organic chemist or an organic chemist in the bad way, um, such that, you're producing heroin, please don't produce heroin. Um, a very simple way is to take morphine that's from, naturally occurring, that naturally occurs in the milk of poppy, and you guys are going to add some type of reagent. So please don't add this type of reagent. And I won't tell you what the reagent is or the sequence of steps. And as long as you guys can convert this alcohol into this functional group, and so real quick before I give the answer away, what functional group is this that I'm circling? So we have a carbonyl group that's covalently bonded to an oxygen, and this oxygen is covalently bonded to another carbon. And so if you guys had said ester, then you guys are absolutely correct. So this is an ester functional group. And if you guys recall how to make esters, it's usually through a carboxylic acid in an alcohol. And so if you guys have, pure substance of morphine, and you let it undergo some type of esterification reaction, you can convert morphine into heroin. So overall, please don't do that. Okay, so now that we've kind of gone over the basics of amines, let's go ahead and talk about how to name amines using the IUPAC nomenclature. So since amines are classified as primary, secondary, and tertiary, there's actually three separate rules for naming amines. And we're going to go ahead and cover all three, but I'll probably break up the video into three pieces. So the first one that we're going to learn how to do is naming primary amines. And so if you guys recall, primary amines have only one R group attached to the nitrogen atom. And so the abbreviation, or the general abbreviation, is going to be RNH2. And so very similar to what we've done in naming organic compounds, we're going to go ahead and find the longest consecutive chain that contains NH2. And so to communicate to the audience or our reader that we have an amine that's present in our organic compound, we're going to name the parent chain, and then we're going to drop the E at the very end of the parent name, and we're going to add the word amine as the suffix. And so if amine is your primary functional group in that organic compound, we're going to number the chain to give amine the lowest possible number. So in other words, our amine functional group gets priority. We want to have the lowest possible carbon number that's closest to the amine. Okay. And last but not least, we need to indicate or communicate to the reader the carbon number of where that primary amine is found. So we're going to go ahead and go through some examples just so we understand how to apply these rules of naming amines to organic structures. All right. And so I'm going to go ahead and first figure out what my parent chain is. And so to figure out my parent chain, I need to find the longest carbon chain. So I have 1, 2, 3, 4. And so it looks like, since I have a 4-carbon chain, I'm going to use the prefix but. And so if you guys look at the bonding between the carbon chain, they're all single bonds, so that's going to be butane. And so we want to make sure that we want to number our carbons so that the lowest possible carbon number is on the amine, the carbon with the amine. And so since the carbon with the amine is this carbon right here that I circled in black, this is going to be carbon number 1, carbon number 2, carbon number 3, carbon number 4. And so since these amines can be found either terminal or embedded within the structure, we need to tell the reader what carbon number that amine is covalently bonded to. And so to complete this name, we need to tell the reader that first of all we're working with an amine. So we're going to drop the E, and then we're going to put butanamine. And we're going to tell the reader that the amine on that butane is on carbon number 1. So the amine is on carbon number 1. So the final name of this organic compound is going to be 1-butanamine. Okay, and we're done. So let's go ahead and take a look at another example. And so here we have a 3-carbon chain, 1, 2, 3, such that we have an amine, so notice that's NH2, a primary amine, that is on the 2nd carbon. So this is going to be 1, 2, 3. Now if you numbered it from right to left or left to right, it wouldn't really matter since in this scenario, this molecule is symmetrical. So this is 1, 2, 3. So notice how the carbon number is the same if we number it left to right or right to left. And so since this is carbon number 2, we're going to go ahead and first name the parent chain. I apologize, part of me just wants to name it, but I have to work it out step by step. So here I have propane, drop my E, add amine, and so what I get is propanamine. And so once I have the name of my parent chain, which includes my functional group amine, I'm going to go ahead and communicate to the reader what carbon number that amine is covalently bonded to. And so currently it's covalently bonded to the 2nd carbon. So I would have to say 2-propanamine. And so that would be my final answer, where if I was trying to draw the structure from this name, I recognize I have prop, which is a 3-carbon compound, and this is telling me that on the 2nd carbon I have an amine functional group. So on the 2nd compound I have an amine functional group. And so the structure, the skeletal structure that I just drew, is reflective of the condensed structure that you guys see here. Okay. All right. So let's go ahead and move on to the next example. And so counting the number of carbons, I have 1, 2, 3. Take 1 back. 1, 2, 3. So in either direction, I get 3 carbons. So that's fine. We're going to go ahead and number them. In this case, if I number it left to right or right to left, I get the same number system on the amine itself. So we want to make sure that the amine gets the lowest carbon number when we, apply the numbering system. And so since it's 2 and 2, left, right, right, left, it doesn't matter which direction we number our carbons, it's going to give us the same answer. So I'll just go ahead and use this one. And so since I have a 3-carbon chain, I know that this is going to be propane. Also, there's no double bonds. They're all single bonds. And so it's propane. I'm going to cross the E, add amine. So this is propanamine. And so we need to communicate to the reader where this amine is found on the carbon chain. And it's going to be on carbon number 2. So I'm going to go ahead and put in 2-propanamine. But we're not done yet because we have one last carbon that is not highlighted. And this is going to act as our substituent. And so since we have a methyl group on the second carbon, we're going to say 2-methyl. And if you guys recall, our substituents always come before the name of the parent chain. And so here we have 2-methyl, 2-2-propanamine. Okay, and that would be the final name of that compound. And so if you guys were to draw this out, I'm going to search for my parent chain. So here I see prop, so automatically I think of a 3-carbon compound. And since I have an amine on the second carbon, I'm going to put NH2 here. And since I have a 2-methyl, since I have a methyl on the second carbon, I'm going to put another line going up. Okay. And so the skeletal structure, my screen is frozen again. So my skeletal structure should reflect the structure that I have at the very beginning. And it does. One is just in condensed form, the other is a skeletal form or skeletal structure. So let's go ahead and look at this example. So here we have our amine. And so we're going to go ahead and figure out the longest carbon chain. 1, 2, 3, 4. Go back 1, 1, 2, 3, 4. So it doesn't really matter which path we choose. We'll just get a 4-carbon chain. And so a 4-carbon chain is going to represent bute. Since they're all single bond, that's butane. Since I have an amine, I'm going to cross out, specifically I have a primary amine. I'm going to cross out the E and then then replace that with amine. So overall, I have butanamine. Okay. And so now that I have the name of my parent chain, I'm going to go ahead and name my substituents. And I'm also going to have to indicate where or what carbon number that amine is covalently bonded to. And so here, I'm going to go ahead and number this left to right. So 1, 2, 3, 4. And then in green, I'm going to number it right to left. 1, 2, 3, 4. And so remember that the priority is the amine, not so much the methyl group. We want to make sure that our numbering system is set up so that the carbon that contains the amine has the lowest value or has the lowest number. And so in this case, 2 is lower than 3 if you guys are comparing these two numbers. And so therefore the numbering system at the top from left to right is incorrect. And so we need to tell the reader that on the second carbon, we will have our amine. And so now that we have the parent chain all sorted out, we're going to go ahead and name the substituent. Here in this case, on the third carbon, we have a methyl group. So this is 3-methyl. And so since we only have one substituent, we're going to add that in the very front. So this is 3-methyl 2-butanamine. All right, so hopefully you guys are, becoming familiar with how to name these amines. Once again, you definitely want to work backwards, and so try practicing how to go from the name back to the structure. And you guys can draw it as the skeletal structure, just so that you guys have an idea to go on how to go forwards and backwards. So remember that this 2 is going to represent the carbon number of where that amine is found. Okay, and so we're going to go ahead and take a look at these examples here. And so looking at this first example, this is just a little bit longer. That's fine. So notice I have a primary amine. I know that I have a primary amine because it's NH2. And so now that I know I have a primary amine, I need to figure out my longest carbon chain. 1, 2, 3, 4, 5, 6, 6, 6. So in this scenario, it doesn't really matter if I want to choose the CH3 at the top, on the left-hand side, or at the bottom. They're all going to give me 6 carbons. So I know that a 6-carbon chain is going to have a prefix of hex. They're all single bonds, so this is going to be hexane. I'm going to cancel this out. So this is going to be hexanamine. So I need to tell or communicate to the reader or my audience what carbon number that primary amine is going to be located on this organic compound. And so to do that, we want to number our carbon chain so that the carbon that contains the amine has the lowest value. And so if we go from left to right, 1, 2, 3, 4, 5, 6, we get carbon number 5 where that amine is located. Let's see if we can reduce that value if we number it from right to left. 1, 2, 3, 4, 5, 6. And so here in this case, it turns out 2 is lower than 5. And so we can go ahead and erase the numbering system that I did at the top and leave the numbering system in green in place. So that's the correct numbering system. And so it looks like I have to put a 2 in front of hexanamine to communicate to the reader that the amine is on carbon number 2. Next, I'm going to name my substituents. And so it looks like I have 2 methyl groups on the same carbon, and that's carbon 5. And so I'm going to go ahead and describe both of those methyl groups as 5, 5, right? So since I have 2 methyl groups, I have to tell the reader that they're both on carbon 5. So 5, 5 dash dimethyl, because I have 2 methyl groups. And so after that, I'm going to scoot this in just a little bit closer and put a dash between the L and the number 2. Remember, dashes have to be placed between a letter and a number. So my final answer is going to be 5, 5, dimethyl dash dimethyl dash 2 dash hexanamine. So let's go ahead and look at this organic compound. So here we have 1, 2, 3, 4, 5. And so with a 5 carbon compound, we know that we're going to be using pent as the prefix. Since they're all single bonds, this is pentane. Cross out the E, we have pentan, and then we need to indicate to the reader that we have amine. So this is pentanamine. Now we need to tell the reader what carbon number that amine is going to be on. And so since amines get the priority, it would only make sense to number it from right to left, so that the lowest carbon number represents, or the amine is on the carbon that has the lowest carbon number. All right, so this is telling us that we're going to have an amine on the second carbon. It looks like we have a bromine on the third carbon, so we're going to go ahead and finish this by saying 3-bromo. So we're going to put a dash between the O and the number 2. So my final name for this structure is going to be 3-bromo-2-pentanamine. All right. And so let's go ahead and talk about cyclic alkanes. And so for cyclic alkanes that contains an amine, we're simply going to name the cyclic compound. So this is going to be cyclopentane. And I'm going to cross out my E and add in the amine. So this is cyclopentanamine. Okay. So I'm crossing out the E and I'm adding the word amine. And so unlike the long chain version, where we typically have to communicate to the reader that the amine is on a specific carbon number, for cyclic rings, very similar to what we've seen in prior lecture videos and prior chapters, if your amine is the only functional group, if your amine is the only the main functional group, then we know that that amine is always going to be on carbon number 1. And so since this cyclic ring will always have an amine on carbon number 1, then there's no need to put a number in front. So typically, one would say 1-cyclopentanamine to indicate that the amine is on the first carbon. Well, since this is a ring, it's automatically implied that the amine is always on carbon number 1. And so the final name to this compound is just simply cyclopentanamine. Okay, so let's go ahead and take a look at this structure. Let me do this in black. I should be doing this in black. Just keep on forgetting to change colors. So looking at this structure here, we have a cyclohexane. And so to indicate that we have an amine that's present, we're going to go ahead and cross this out. And we're going to add in amine. And so here, we're going to go ahead and carry this part down, this cyclohexane. So this is going to be cyclohexanamine. And that would be the name of the parent chain. And so it looks like we have a methyl group. I'm sorry, not a methyl, an ethyl group. So we have 1, 2 carbons. And so since this carbon here is always going to be carbon number 1, we want to number our ring such that our substituents will get the lowest possible carbon number. So this is going to be 1, 2, 3. And so it makes sense to number our ring clockwise. If we did it counterclockwise, we're going to get a number 5 on where that ethyl is, which is greater than a 3. And so to finalize this, the name of this compound, we're going to go ahead and say 3-ethyl cyclohexanamine. And so this is not the full year of organic chemistry. If this was the full year of organic chemistry, then we would have to take, we would have to communicate to the reader the spatial orientation of the NH2 relative to this 2 carbon group. And so if I kind of erase this portion right here, notice that this is a wedge line. So this is telling us that this NH2 is pointing up. And so with cyclohexanes, we can look at the edge. And if we look at cyclohexanes at the edge, we get something that's known as a chair conformation. And so this is like the 3-dimensional structure of this cyclohexane when we were looking at it from its edge. And so since the NH2 is pointing up, I can just choose like a random place, and let's just say that this is where the NH2 is. So notice that it is pointing up. And it is 1, 2 carbons away from the ethyl group, so 1, 2 carbons away. And this ethyl group, since it has a dashed line, is pointing down. Okay, so that's my ethyl group right there. And so if this was the full year of organic chemistry, we would have to communicate the spatial relationship or the spatial orientation of NH2 and this ethyl group. And so we would say that they're trans. But we're going to go ahead and leave that out. I just wanted to throw that out there for the viewers who are watching this video who are not in Chem 104, who are not in my Chem 104 class. All right. So let's go ahead and just look at one example of, or maybe a couple of examples on how to name these primary amines, these organic compounds with primary amines that has a double bond. And so I'm just going to use this structure. This is something that we've already named in the previous lecture slide. And so I'm just going to add a double bond here. Okay. So how would you name an amine with a double bond? Well, once again, we have to indicate the number of carbons, 1, 2, 3, 4. And so here in this case, we have a 4-carbon compound. And so we're going to get bute. Now, since there is present a double bond, this is going to be butene. And so since I have an amine, very similar to the butane version, I have to drop the E, and I have to add amine. And so this is butenamine. Now I have to communicate to the reader what carbon number that double bond starts at and what carbon number that amine is bonded to. And so since I have two things to describe all on the parent chain, I'm going to go ahead and separate out this amine from the En. Remember, the En represents the double bond. And amine is the amine, the functional group. NH2. It's primary. Okay. And so if you put a number in front of butane, then that number is going to represent the carbon number in which the double bond starts. And so let's look at numbering this guy. And so if you have a double bond and an amine, the primary goal is to make sure that the amine has the lowest, the functional group has the lowest carbon number, even though there's a double bond present. So this is going to be carbon 1, 2, 3, 4. And so on carbon number 1, we're going to have our amine. And so we cannot put a 1 here because this 1 is going to refer to the double bond. And so what we're going to do is we are going to put the 1 in front of amine. Okay? And so this, by doing it this way, we're communicating to the reader that the amine is found on carbon number 1. And so I want you guys to notice that on carbon number 2, that's where our double bond starts. And so therefore, I'm going to put a 2 in front of butane to communicate to the reader that the double bond starts on the second carbon. Okay. And so this would be my final answer for this specific compound with a double bond. This is 2-butane-1-amine. And so once again, if you're trying to draw this out, since I have a but, I know that I have a 4-carbon compound, 1, 2, 3, 4. And on the first carbon, I have an amine. So if this is carbon 1, I need to make another covalent bond, then put my NH2. And so since I have a double bond that's on carbon 2, then on carbon 2, I need to put a double bond. And so overall, my skeletal structure will yield something similar to my original structure that I named. Okay. All right. So let's go ahead and look at another one. Let's say that we have 2 double bonds. Let's go crazy, right? And so here in this case, I have 1, 2, 3, 4. So I'm not breaking my octet on that carbon. And on this carbon, I have 1, 2, 3, and 4. So by placing those double bonds on this ring, or not on the ring, on this organic compound, I'm still following the octet rule and I didn't break it. So this is a valid organic compound. So let's go ahead and count the number of carbons. We have 1, 2, 3, 4, 5. So a 5-carbon compound is going to have the prefix pent. So this is going to be pent. Now, the fact that I have 2 double bonds, I need to put in ene, pentene. But since I have 2 double bonds, I need to put in penta diene. Okay. And so this is this presence of two double bonds. That's something that we covered in chapter 11. So pentadiene. And so since I have an amine, I need to cross out the last E and then put in an amine. So this is pentadiene. Okay, great. And so we don't want to be married to the way that we've kind of named this compound just yet, because we need to communicate to the reader what carbon numbers or what carbon these double bonds and these functional groups are found. And so since the numbering of these carbons is on the parent chain, we have to separate the double bond from the amine. And so if we want to number our carbons, we want to make sure that our amine gets the lowest possible number. So if we do this from left to right, we get 1, 2, 3, 4, 5. And if we go from right to left, I get 1, 2, 3, 4, 5. So since 2 is less than 4, then we are going to erase the numbering system in blue and keep the numbering system in green. And so this is going to tell me that I have an amine on the second carbon. And so where the amine is located, directly right before it, that gap, I'm going to put the number 2. So this is going to be -2 -amine. So that's telling me that on carbon number 2, I'm going to have an amine. So here I have diene. So that means I have 2 double bonds. And I need to communicate to the reader what carbon number those double bonds will start at. And so looking from right to left, already at carbon number 1, I have the beginning of a double bond. And on carbon number 3, I have the beginning of another double bond. And so this is going to be 1, 3 pentadiene 2 amine. Now we're not done yet because we have a bromine that's present on carbon number 3. And so we're going to extend the name to include the substituent. And so since we have a bromine on carbon 3, we're going to say 3-bromo -1, 3 pentadiene 2 amine. Okay. And so that is going to be the name of my organic structure with 2 double bonds. And so it looks complicated, looking at the outcome, it's like, whoa, that's a long name. However, if you guys just take it, piece by piece, step by step, start with your roots and then kind of build it up, then you guys will eventually get the name of this compound. Okay, and so hopefully you guys understand how to name these double bonds for these linear chains. We're not going to do it for this ring structure. That's fine. That's pretty much it for this lecture video. In the next lecture video, we are going to look at how to name secondary amines. See you guys.